Hi, welcome everyone to our seminar today. We are very happy to have with us Andrzej Szulkin from the University of Stockholm. Andrzej is a researcher working in nonlinear functional analysis, and he's particularly an expert in topological and variational methods in functional analysis. So we are very happy to have him today, and he will talk us about a Sobolev-type inequality for the curl operator and ground states for the curl-curl equation. Thank you very much, Andrzej, and you can begin with your seminar.
Well, first of all, I would like to thank Alberto and Monica for inviting me here and for the opportunity to giving this talk. I have been in Mexico many times, but before COVID, and now it's my first time after COVID. So what I'm going to speak about today is a joint work with Jarosław Mederski from the Polish Academy of Sciences in Warsaw. And let me first, let me first start by saying a few words about the Sobolev inequality. So what it says is that there exists a constant such that the integral of the gradient square of u is bigger than or equal to this constant, and now the L2 star norm to the power 2 by 2 star. And now the notation that I use here and will be using throughout the talk is 2 star is the Sobolev constant, is the critical exponent for the Sobolev inequality. And I will use the LP norm. I will use single bars for denote the LP norm. And now D1 to 0 of omega is the closure of C0 infinity with respect to this norm. So we have gradient U L2 norm. And D12 of Rn or U, which are in L2 star, such that the L2 norm of the gradient is finite. And in Rn, in fact, these two spaces coincide. And 2 star is known to be the critical Sobolev exponent in the meaning that D12 of Rn is can be embedded in L2 star, but not in LP for any P, which is bigger than 2 star. Okay, so this largest constant C is called the Sobolev constant, and one can define it as the infimum of the L2 norm of gradient U squared by L2 star norm also squared, and one can either take all U which are test functions or U which are in D1 to 0. So let me recall a few well-known facts. First of all, S is independent of omega. And also S is attained if and only if omega is the whole of Rn, and U is equal to some constant times this function. And this function, it is a well-known function. It's called the Oben-Talenti instanton, and these functions are the only positive solutions to this equation. And here, well, Y is just the center of the well, U epsilon Y is kind of a bump, and epsilon and Y is the center of this bump, and if epsilon goes to 0, then these functions will concentrate more and more. Also, what is known is that U epsilon and Y are ground states, which means that they are non-trivial solutions which minimize the energy function of J of U. Also, another thing of, or one way of obtaining a ground states is one can minimize J over the Nehari manifold, which by definition is the set of function U with 0 deleted such that J prime U evaluated at U is equal to 0. And a simple computation shows that J1 UU equal to 0 is exactly the same as this equality. Also, on N, one can simplify JU. One can get rid of this term, and then J of U will be equal to this function. Now, if V is not equal to 0, then one can choose U equal to CV, and one can choose C, a unique C bigger than 0, such that CV will be on the Nehari manifold. And then one has this quotient equal to this quotient, and again, a simple computation shows that this is equal to the L2 star norm to the power 2 star minus 2. And it's also equal to Nj of U to the power 2 by N. And now if one takes the infimum on the left-hand side, then one will get S, the Sobolev constant. And one will also get an infimum here. So in other words, this will be equal to the Sobolev constant if and only if U is a ground state. Now, from now on, I want to have N equal to 3. And well, my goal in this talk is to see what happens if one replaces the gradient U by curl U. And one also wants to have the property that some constant, which I call S curl, is attained if and only if U is a solution to this equation. And note that 6 is equal to 2 star. So here we have 2 star to the power, 2 star, U to the power 2 star minus 2 times U. Well, there is one obvious candidate. One does the same thing as before. So instead of having gradient U, we take curl U and divide by the L6 norm squared of U. But this is not a good choice because curl U can be equal to 0. So this means that the infimum will be equal to 0. So also, why is it interesting to replace gradient U by curl U? So let me give a physical motivation for that. Well, we start with Maxwell's equations. We have a dielectric and non-magnetic and charge-free medium. Then Maxwell's equations look like that. Well, if the medium is conducting or magnetic or not charge-free, there will be still 4 equations, but right-hand sides will be a little bit more complicated. And here E is the electric field, B is the magnetic field, and D is called the electric displacement field. And we have two physical constants, and also another important quantity is P, and P is given by this constitutive relation. So D is equal to epsilon 0 E plus P. And now, if we take curl of this, so we will have curl E. So we will, here we will have the T derivative of curl B, and we can insert curl B equal to this. So the equation will look like that. And after some simplifications, and it will be equal to, or after not simplifications, but replacing D by what it is, we will get this. And also another thing which is sometimes useful is that curl E can be written in this way. So now, after collecting terms, we have this equation, or in fact, it's a system of three equations because it's from R3 to R3. And now a remark is that if there is no polarization, for example, if we are in vacuum, then P is equal to 0. So divergence of E will be equal to this, equal to 0. So divergence of E is 0, meaning that this goes away, and we have minus Laplacian E equal to this. And this is a wave equation in R3, so it's very well known, and it's, it has explicit solutions. Now let us also suppose that the electromagnetic wave is a time harmonic with a single frequency omega, and we insert ext equal to x e to the power I omega t, and the same thing for px, for the polarization. Then what we get is this equation. And now, up to now, everything is linear. But now we make an assumption, which is usual, that polarization is a nonlinear function. So this is how nonlinearity will enter here. This function epsilon is called the dielectric response function. And usually one has EXS equal to, just two terms. And now if if E is light, if the intensity of light is small, then one can neglect this term, and the dielectric response P will be, or the dielectric response E will be linear, and the system will be linear. Also, another case which has been studied a lot in physics is P equal to 4. It's called the kernel linearity. So here we have s to the power 1, and here we have e squared. So it will be something, it will be, P would be something like e squared times E. And what this really means is simply that one develops E, one takes a Taylor expansion of E. This is the first term, this is in this case the second term, and one neglects the rest, the other terms. So now, because of this derivation, it is reasonable mathematically to consider this equation. So here we have some v of x, and here we have f of xe, where f is the derivative of capital F. Now, this can be, in fact, this equation can be reduced to a semilinear Laplace equation. One can either make what is called the scalar approximation, so one neglects this term, and this is often done in when considering wave propagation and waveguides. And the problem is, well, this makes things easier, but on the other hand, it is known that it can sometimes produce solutions which are not physical. Another possibility is imposing critical symmetry, cylindrical symmetry. So we take R is the length of the vector x1, x2, and E of x is equal to U R x3 times this vector. And then one has that the divergence of E is 0, so curl E simplifies to this. So one has an excuse me, an nonlinear Schrödinger equation or a system of equations, and this can be treated by usual methods, and here there are papers by Stewart and co-workers, and also Azzolini, Benci, D'Aprile, and Fortunato. And the full curl equation, in fact, it became tractable only recently, and the first paper is the one by Barch and Medersky. It appears, well, it's now 8 years ago. So now let me introduce the variational setting for the problem. Now I suppress V, either V is 0 or it could be included in F. So I have this equation, and U goes from R3 to R3, and F is the gradient of F, of capital F. So formally, the solutions are critical points of this functional. And we always assume that F is strictly convex in U. In fact, if this assumption is dropped and one has full curl equation, then absolutely nothing is known. So now, for the quadratic part, note that curl U squared can be replaced by this or by that. And here one sees very well that the kernel of curl U is in fact equal to is infinite dimensional. Now one has what is called a Helmholtz decomposition. So one has two parts, V, which is divergence free, and W, which is curl free. Now, if W is curl free on R3, then it is well known that is gradient of some function Z. So one can replace, so if one takes curl of W, it will be 0. Therefore, one has this equality, and finally, V is divergence free, so one can replace curl V by gradient of V. So the kernel will be of this quadratic form will consist of all functions which are gradients. And now, to introduce an appropriate space, well, this is in fact dependent on the choice of the function capital F. Here I want to consider the critical exponent case. So for us, F will always be equal to 1/6 of u to the power 6. And we consider this problem. This is what I mentioned at the beginning. Now let omega be a domain with smooth boundary, and omega equal to R3 is allowed, and in fact, this is the case I will focus on through the main part of the work. And now an appropriate space is what is called W6 of curl omega. So we take U in L6, recall 6 is 2 star, and the curl of U is in L2, and the natural norm is the L6 norm U squared and curl U L2 norm squared. But also another space which will be important is W60, which is the closure of C0 infinity in W6. And what one can show is that W06 and W6, that they coincide on R3. Now we will need two subspaces. One is V omega. Well, the definition looks quite complicated, but I will explain it in a moment. And also W omega, well, this is simply functions in W06, whose curl is 0. And concerning V omega, now locally we have that phi is equal to the gradient of psi. So if we take, well, if psi has small support, phi, or if take phi of small support, we have gradient psi. So if we integrate by parts, we will get curl, we will get a divergence of V here. So divergence of V is 0, and we also have that the L2 norm curl V is equal to the L2 norm of the gradient of V. Also, one can show that if omega is bounded and simply connected and has connected boundary, then V omega is in fact the set of V's such that which are divergence free. So in this case, curl is the direct sum of the curl free part V omega and divergence free part V omega and curl free part W omega. And in general case, in fact, it turns out that W omega will include some functions which are divergence free, so both kernel free and divergence free. And one can show that this subspace is at most finite dimensional. But for the sake of simplicity, assume that we have this condition. So now for the moment, I want omega to be equal to R3. Then we have W is a gradient of Z, X is the sum of these two parts. And the norm of U is L2 norm squared of gradient V, L6 norm squared of W. And what is important here is that W is a subspace of D12. So now I want to introduce S curl of omega. well, we have u in W06, so it's a closure of a function of a C0 infinity. So we can extend u by 0 outside omega. And now we define S curl omega as the largest constant C with this property. So we would like to have here u, but then C would be 0. Instead, we take the infimum over OW, which are in capital W. And here, in fact, we take all u, which are here, and in fact, one can also include u in W, then we would have 0 bigger than or equal to 0. But here, an important thing to observe is that u is supported in omega, but W may not be. So we can take infimum over W, which are defined on the whole of R3. So, and now taking u here, we take W of u as the minimizer of this expression. And well, it exists and is unique because on L6, this functional is coercive and convex. And also u taken to W of u is continuous. And using this, there is an alternative characterization of S curl of omega. So we take infimum of u here, and we take curl u squared divided by u plus W of u. And if I denote S curl by S curl of R3, there is a lemma saying that S curl is in fact bigger than the Sobolev constant S. Well, first one shows by easy calculation that S curl is bigger than or equal to S. This is a, well, essentially this is by Hölder and Sobolev inequalities. And now to obtain the strict inequality, one shows that S curl is attained, and the function attaining S curl cannot be an instanton. So S curl is strictly bigger than S. Now there is a theorem saying that S curl of omega is equal to S curl for all omega in all smooth omega contained in R3. So S curl is independent of omega. And well, in one direction, this is easy because this is a subspace of this. So we get S curl less than or equal to S curl on omega. And the reverse inequality is in fact definitely much more difficult to show. And I will not discuss this in this talk. Now also one can define another Sobolev constant, S curl of omega. So it's the same inequality as before, but with one important difference. Here we don't take W in the whole W omega, but we take we don't take a W in the whole W, but we restrict W to W omega. So in this case, U is contained, is supported in omega, but also W is supported in omega. So this is the difference. And now this constant, S curl bar, is more natural if one works in omega. but it is more difficult, in fact, to work with. One would prefer to have this constant, but there is a price for using this. Well, what we have, and S curl is equal to S curl of omega for O omega. And it's bigger than the Sobolev constant. And we also know that S curl omega is bigger than or equal to S curl bar of omega. And for bounded omega, it is bigger than or equal to S. So we don't know if they can be different. Well, we believe they are not, at least not for smooth omega, but we were not been able to show this. Now, I want to give some brief explanation why S curl is attained in R3. So we have this decomposition, and WV is the minimizer. So now a very important step here is a theorem which says that if Vn is going weakly to V0 in V, then passing to a subsequence, one has WVn going weakly to WV0, and also it goes to W of V0 almost everywhere, and also in LP log for subcritical P. This last thing is not at all obvious because we are working, for W, we are working in L6. So weak convergence in L6 does not imply almost everywhere convergence. And now the idea of the proof is that, well, first, we can assume Vn goes to V0 almost everywhere. Also, we have a weak convergence in measures. Gradient Vn squared weakly converges to some measure mu, and Vn to the power 6 to another measure rho. And now there exists an at most countable set J with non-negative weights such that mu is bigger than or equal to this, and rho is equal to this. And this is in fact exactly Pierre-Williams' concentration compactness principle. Now we have that Vn bounded implies W of Vn bounded. One has to prove this, but it's not difficult. So passing to a subsequence, WVn goes weakly to W0. And now, since J is at most countable, we can remove open sets of arbitrarily small measure. And after doing this, one can show almost everywhere convergence outside of this. And now one takes K to infinity and taking subsequences, and one uses a diagonal procedure, well, like in the Arzelà-Scoli theorem, we obtain that this goes to V0 plus W0 almost everywhere. And finally, one shows that W0 is equal to W of V0. And now, in our case, we have J of U equal to this. Curl U can be replaced by gradient V. And it is easy to see that J is of class C1, and critical points of J will be solutions of this equation. So now let me introduce what is called the Nehari-Pankov manifold. So this is like in the Nehari manifold, but we also want J prime U W to be equal to 0 on the subspace W. And now by known results, one can show that if infimum is attained, then the minimizer or ground state solutions. So what remains to be shown is that the minimizers, in fact, the minimum is attained. And here I think that I will have to skip some parts of the talk. Let me just briefly say that we have J of U equal to this, and W of V is a minimizer, so we have J prime U, W of V equal to 0. So for W of V, this is satisfied. And finally, one chooses an appropriate T to get the maximum here. And for the maximum, we will have J prime U equal to 0. So now S curl is equal to the infimum of this, or curl U can be replaced by the gradient of V, and instead of taking the maximum of U here, we simply take V plus W of V here. So now S curl is equal to this infimum, and now one shows that this, well, this is the same as this, because TV plus W, W of TV is equal to T W of V. And by a simple computation, one can show this. So what remains, well, here, if one takes the infimum, we get S curl. And if one gets the infimum here, if the infimum is achieved, we will get a solution to the curl equation. And now I think, in fact, I will have to skip this part. Let me just simply say that one shows that the infimum is attained. So what we get is what we get is a solution to the curl equation with a critical exponent. And this says also that S curl is attained. So now the question is, can S curl omega be attained on omega, which is not equal to R3? Well, we conjecture it cannot. Recall that for the Sobolev constant, this is not the case. S of omega, S is attained only on Rn. So if S curl were attained for some U, we can extend it by 0, since they are equal. So you would also solve this equation in R3. So in particular, if omega is bounded, we would have a solution, a ground state which has compact support. Well, we found no unique continuation principle which would rule out this possibility, but we don't believe this can happen. And now there is also a Brazil-Nuremberg type result, which I think, how much time do I have?
At least 15 minutes.
Okay, so let me perhaps very briefly say that, well, the known result of Brazil and Nuremberg is that this critical exponent problem has a positive solution if lambda is less than the first eigenvalue and n is bigger than or equal to 4. And for n equal to 3, 0 should be replaced by some lambda star. For lambda less than or equal to 0 and omega star shape, there are no non-trivial solutions. And also this Brazil-Nuremberg result has been extended subsequently to all lambda bigger than 0 if n is bigger than or equal to 5, and to all lambda which are not eigenvalues if n is equal to 4. And in fact, very recently, I saw a paper which claims that also that this can be deleted also for n equal to 4. So now what we consider here is the boundary value, this boundary value problem. And here one has nu, which is outer unit normal, and nu cross u should be 0. Physically, this corresponds to a situation where omega is surrounded by a perfect conductor. So in omega, there is no field, no electric field E. And the functional would look like that. So here the extra term is this one. And now if one looks at this eigenvalue problem, well, the first eigenvalue is lambda 0 equal to 0, and the eigenspace is the whole of W omega. And now V omega is contained in H1 omega R3. Again, this is important that omega is smooth. I will come back to this. And divergence V is equal to 0. So our eigenvalue problem looks like that, and it's on a subset of H1. So there exists a sequence of eigenvalues, lambda 1, lambda 2, and so on, going to infinity. And now let me just show you the theorem that if minus lambda is contained here, well, we assume minus lambda is less than lambda k minus 1, bigger than lambda k minus 1, and also here. So then this equation has a ground state solution, and the ground state level will go to 0 as we approach lambda k from the left. And here, let me also mention a challenging problem. There exists non-trivial, well, whether there exists non-trivial solution for what is called cubic quintic nonlinearity. For the Laplace equations, there are some there are some results. Here I mentioned one of them. And it says that if omega is in a proper interval, then there will exist solution, or there will exist ground states, but not otherwise. And now I want to, at the end, I want to discuss a few open problems. First of all, this I already mentioned. Does there exist a ground state whose support is a proper subset of R3? As I told you, we don't believe this can happen, but it's an open problem. Another one, can one find an explicit expression for a ground state? Well, for a ground state for the plus equation, one can, but here we don't know. And at least can one say something about the decay property of ground states? And it would be good to know that are the same as for the Aubin-Talenti instantons, because then one could hopefully look for equations where the right-hand side consists of this, and some monotone lower order perturbation. But we don't know. Another thing, do the ground states have any symmetry properties? Are they regular? Are they continuous? Also, if one presupposes some symmetry, there are certain results which says, in the case of radial symmetry in the first two variables, then one knows that there exist ground states, but with this symmetry, but it's unclear whether they are the same as our ground states. And the regularity property. Another thing which is interesting, well, if one takes a bounded domain and it's neither convex nor C11, then one can show that V omega is in HS, where S is in this interval. And in fact, S can be strictly less than 1. I think there's an example where S is exactly equal to 1/2. Well, this is, in a sense, hard to believe, but since there are examples, one has to believe in that. And now suppose that S is strictly less than 1. Then the critical exponent is strictly less than S. What does this mean for the results of the Resumen type? And finally, well, this inequality, we have this inequality. Well, here we know that S curl is bigger than S, but we don't know for S curl omega. So can one somehow get something better? And also, if one takes a domain like NP4, can one get S curl bar less than S? Well, it's unclear, and in fact, I believe one cannot, and Mederski believe one can. So I leave this question open, and I think this is the end of my talk.
Thank you. Thank you very much, Andrzej, for a very nice talk, very interesting. Are there any questions for Andrzej? Please feel free to open your mic and just ask.
I have a question. Andrzej, I was wondering, I mean, what is behind the fact that for the best Sobolev constant, the best Sobolev constant is the same for Rn and for a bounded domain or any domain in Rn. And here you have the same for this S curl. So is there some geometry behind it? Because for the best Sobolev constant, what is behind it is the invariance on the dilations and translations. So is there something similar for this S curl constant?
No, S curl without bar is equal for each omega. Yes. But S curl with bar, we don't know.
Yes, but my question is, why is it the same? Is it the same because there is some special geometry behind it? like invariance under dilations or invariance under translations, because this is what makes the constant, the Sobolev constant, the same for a bounded domain and on an Rn. So my question is, for the S curl without the bar, you say S curl without the bar of omega is the same as S curl of R3. So why? Is there some geometry behind it?
Well, not really. It's well, you can make dilations and but well, you have this V on which you can easily make dilations, and you have this W of V. You can still make dilations, but this is not at all straightforward.
But then if you can make if the W is invariant on the dilations, this could explain why this S curl is the same. No?
Well, it's, the curl instanton is invariant by dilations.
Okay. Okay.
Well, equation is invariant by dilations.
Okay, so this was my question precisely. Yes.
Yes.
Are there some other questions? I have a question regarding your question 3, which is what are the symmetries of the ground state? Do you have any conjecture, or what kind of symmetries do you expect, or what kind of symmetries you don't expect? Have you thought about this?
Well, there is one thing that there are. It is known that all solutions which are radial in R3 are trivial, so there is no room for radial symmetry. But if the solutions are radial in 2 dimensions, well, it's not so clear, and I don't really know what to expect.
Do you think that maybe the picture is also like the one from the Talenti functions in the sense that there is only one that up to some transformations give you all possible solutions, or you think here that the picture could be a little bit more complex?
Probably not, but it's again, it's not clear.
Yeah, it seems like a difficult problem.
Yes.
Without the symmetries, you lose the ODE techniques, which is what, in a sense, are determining the Aubin functions.
Well, the ODE technique you cannot have because
you're not radially symmetric. Yeah.
Yes.
Well, thank you. Any other questions for Andrzej?
Yes, I have one.
Please go ahead.
Okay, about the Helmholtz decomposition that you use in R3, when you go to a bounded domain, you also have that the core is equal to the gradient in.
Pardon?
Well,
could you repeat the question?
When you work in a bounded domain, you can also use that the core is equal to the norm of the gradient. Because
yes.
you use several times that trick.
It's well. In fact, I don't know. We don't use this.
Because I was thinking in the Helmholtz decomposition, not in R3, you don't have uniqueness of this decomposition. You have an extra term plus the gradient of something else.
Oh, well, one always have a uniqueness of decomposition. Let me go back. It's at the beginning. Well, you have uniqueness of the decomposition. So here X would be V omega plus W omega, but on domains which don't satisfy this condition of simple connectivity and connected boundary, you still have this, but you can no longer, a part of W omega will also be divergence free. But still, if you define V omega this way, the decomposition will still be unique. Is it an answer to your question?
Yes, thank you. Yes, thank you.
Are there any other questions? If that's, let me see the chat. If that's not the case, then we can all thank Andrzej for his very nice seminar. Thank you, Andrzej.